Everyone just assumed I died, yeah. Everyone's just like, oh, he's gone now. They're like, oh, I guess it's Parker's time to teach this class. We're just going to move through the organic people as we all die or something similar. Okay. We are set up. I remembered my lunch today. I forgot my lunch Monday, but in turn, remembering one thing, it meant I had to forget my power cord for my computer. So I can only apparently remember one thing at a time. One thing. It's like, oh. And Butner needs me to do stuff today, so I get to borrow his power cord because if my computer dies, I can't do the thing he needs me to do. So I can, like, strong arm it. I'm just going to leave early. So there's no lab today. No research this week because I was gone for 2 days. Okay. We'll wait on Caitlin for a few, since I told her she didn't have to stay on the call. She should be here shortly. So we're going to start off with the Sonic-Ashira reaction. We're going to start with the catalytic cycle because it's related to the other cycles we've been doing. So that's where we'll start. So whatever slide that is, slide 28. This weekend I will miraculously make you more slides on olefinations, and we'll get there. So yeah, we'll give Caitlin a few here. I'm not in no fire hurry. Gotta milk these slides for all they're worth. I just feel generally hotter with the mask on. Yeah. I don't know, like, I'm a sweaty, disgusting mess normally, but like I just feel like it's like cranked up to 11. I'm like, I know dogs cool themselves by breathing out of their mouth. Like, do people do the same thing?
It's like the heat that you exhale is just like trapped.
Yeah, I'm just like, I'm like a little face sauna, and I'm like, and the my response is back sweat. And it's just like, damn it, stop. Body, this makes no sense. Is this better than face sweat? Maybe. Here, I will share a screen. You guys don't have the whiteboard. And we have a Caitlin, Sans Coffee, pouring out for her homies the coffee cup who couldn't be with us today.
I am so sad I spilled my coffee. You don't understand. I literally was walking perfectly fine, and then it just like, I don't know, fell out of my hand. I don't understand.
This is awful.
I'm coffeeless. I'm really sad.
I am sorry.
I had like 3 sips of it. I'm really upset right now. It was good too.
It was good coffee?
Yes, it's a caramel macchiato.
It's basically just a milkshake with caffeine in it.
Yeah.
Yeah. Okay. I don't drink coffee.
Well, I have to have coffee and an energy drink every day or I don't function.
Have you gone to bed earlier? Have you like given that one a go?
I did.
What time did you go to bed?
Well, okay, not last night, but the night before I did that. I went to bed at 11. That's pretty early for me.
Yeah.
I still woke up tired, and I still had coffee and an energy drink, so it did nothing. I didn't sleep.
So we're going to talk about the Sonic-Ashira reaction. This is kind of the next or the last in our like cross-couplings. Try to spell this right. So the difference here between all the other ones is here you end up taking the halide, whatever you're using, an alkyne, and you use palladium plus a copper salt. It's copper 2. It's copper 2. We'll see in a second. And you end up adding an alkyne. So this lets you do a couple of sp2 carbon to an sp carbon. Oops, right. What type of copper salt this is? Oh, copper 1. I bet. Copper 1. There's a big distinction. So the reason you need the copper is that these also are going to have a base in them as well. We're going to have our base. And the point of the copper is the metal that we transmetallate with our palladium-2 species. So you take your alkyne, whatever it is, and in the presence of copper X, so X being usually Br or iodine, copper chloride could work, right? And base, your copper end up on the end of your alkyne. It will replace the hydrogen at the end of your alkyne. So copper likes alkynes. So copper will associate itself, will have a weak interaction with the triple bond. And what that does is that interaction makes the alkyne hydrogen more acidic. So that hydrogen usually can't be deprotonated by something as like a trialkylamine, like triethylamine, that's usually not basic enough. But the fact that your copper binds to the triple bond increases the acidity of that hydrogen and allows your amine base to grab that hydrogen. And then, through the magic of inorganic chemistry, you'll end up with the copper on the end, and you'll make an ammonium salt. Right. So this is our metal that we need to transmetallate with. So this is kind of the extra step in the Sonogashira, right? Everything else is kind of the same. We have to make our organometallic that we do the transmetallation in the reaction itself. We don't just get to take it off the shelf. We just have to make it in situ. So we make that during the reaction. So all the other steps are exactly the same, right? Again, you'll have this down. You'll be able to do this in your sleep. We will have our palladium 0, whatever that is, insert into our carbon halogen bond, right? What's that called when you do that? When palladium inserts into the carbon halogen bond,
Oxidative insertion?
it is oxidative insertion.
Wow. Didn't expect to get that out.
Right? You are inserting your palladium into a bond, and it oxidizes. It loses electrons. Right? It goes from 0 to palladium plus 2. So that is our kind of our oxidative insertion step. I guess that should be like there are ligands on this, but whatever. Then we have that copper acetylide that we made previously, right?
Does it say below PD?
LN. So ligand. So those are the ligands. So when we look at the one that's a little bit neater, everything's going to have LN, which is just some number of ligands. Depending on what ligand you started with your palladium, your palladium is going to have one of those ligands. It can have two of those ligands. It can't have more than 2 normally, because palladium only has 4 sites on it that it can hold things. So when you do your oxidative insertion, 2 of those positions on the palladium are taken up by the halide and the carbon group. So one or two of those sites can then be taken up by the ligand. And so it just changes ligand to ligand, but it doesn't impact the reaction mechanism at all. Because, like, honestly, we don't care how many ligands are on the palladium as long as it doesn't crash out of solution. As long as it stays soluble, we're happy people. So this is my copper acetylide that we made at the bottom of the other slide, right? So this guy right here, that gets in the reaction, by doing this down here at the bottom, right? So that's happening off to the side, the catalytic cycle. And then we do our transmetallation, where we now have our palladium with its ligands on it, have an alkyne. Okay, you're going to make copper X. So whatever the halide is here, that's the halide here. That's the halide the copper ends up picking up. Right, because the copper's basically trading its carbon group for whatever the halogen is on palladium. Right, so this is our transmetallation. Right, and then we have the same last step that all of these have had. The palladium's holding two carbon groups. It sticks them together, makes your bond. And generates palladium 0 with ligands on it again. And the last step is called when we have the two groups and we stick them together. That's what's the cross coupling is the whole thing. What is the name of that step? Reductive elimination. You eliminate the palladium from the molecule and you regenerate, and you go from palladium plus 2 to palladium 0. So you reduce your stuff. So this is reductive. So the prettier version of this is, right now I gotta do a new share here. Right, the prettier version of this is what I have on the screen. Right, where you have your, at the top you have your palladium 0. And we generate that. We can either start with palladium 2 and have the phosphine reduce it, or the palladium 2 reacts with the copper acetylide, and then get our palladium with our ligand on it. And then this is where we actually just drew through. Oxidative insertion gives us our palladium with our R group on it, and then our halide. Transmetallation over here in this corner is where the copper acetylide is getting made. Right, then we do transmetallation. Then we have this, and then we do reductive elimination, which gives us our product and gives us back our palladium 0. All right, so that is the whole reaction. So, excuse me. Here's a few examples, right? Ortho-iodo-aniline. And you can couple that with this alkyne. What's nice is you're not using strong base, right? You're not using like hydroxide like in Suzuki reaction or anything. So like you can have an unprotected oxygen, right? We're not using N-butyllithium or something that's going to deprotonate that. So we can just use unprotected groups, esters, and we can cross-couple that on. And then there's a whole class of chemistry that we may or may not cover that is gold catalyzed, where gold just acts like a really big proton. it just acts like a big positive charge, and then that allows us to turn this alkyne into an indole. And then here's a simpler one. Do I even have it on here? Oh, I didn't have the alkyne. Sorry, the alkyne is just this right here, and you just couple that on in good yield. So these are pretty simple examples. There are more complicated ones, but the basics are the things you're looking for here is, do you have a copper 1 salt? Right, all of these have copper iodide. Right, do you have a copper 1 salt? Do you have an alkyne? Do you have palladium and an aryl halide? And it's going to let you know that you're doing a Sonic-Ashira cross coupling. So far, so good? Okay. Now we've come full circle. We're not back to my molecule. We're going to finish this off. Right? So you guys already know this reaction. Right? TBAF, if you remember from Organic 2, removes a protecting group. So it takes silicon protecting group and knocks it off, right? Because silicon likes oxygen, but it likes fluorine more. TBAF is a source of fluorine that doesn't melt your bones. So we remove, oh no, I don't have the starting material. I was so prepared, then I wasn't. Is where do we leave off? This is what we're starting with. There we go. So it has this TBS protecting group and this TMS group. So we start the sequence by removing both of those, and then we oxidize that alcohol with manganese oxide again. Right? It oxidizes allylic alcohols and benzoic alcohols to this aldehyde. Now, this next step is kind of interesting. It kind of goes against everything I taught you in Organic 2. But here we go. So, what is more reactive to like addition with a Grignard? An aldehyde or a ketone? If you have an aldehyde and a ketone in a molecule, and you want to add a Grignard to it, let me actually draw it. Quick, new screen share. All right. So let's say you had my kind of stock Organic 2 molecule here, and I had a Grignard reagent. Which of these two groups, the aldehyde or the ketone, is a Grignard reagent going to add to first? Which is easier to get to? Yeah. So you can normally say that if you have an aldehyde and a ketone in the same molecule, that you're going to prefer to add to the aldehyde first, right? So if I use only one equivalent of this, the product I would expect to make would be the product where the Grignard reagent adds either exclusively or predominantly to the aldehyde. All right. So I had, in my little reaction here, am I going to get PowerPoint back? Okay. So I had an aldehyde. I had an aldehyde and I had a ketone. I was like, sweet. I know what I'm going to do. I'm just going to go get vinyl magnesium bromide. I'm going to add this. It's going to take like 10 minutes. I'm a genius. That did not happen. What happened instead, back to sharing another screen. What happened instead was, so the molecule looks like this. I think this is instructive just for like things to think about they kind of go beyond just basic reactivity of things. That's kind fugly, but whatever. Great. So you remember, part of the reason we wanted to do, what's it called? Sulfur was because sulfur had longer bonds and could relieve strain. There's actually a reasonable amount of strain on this carbon, being sp2 there. So even though this is an aldehyde and it's conjugated, right? It's conjugated to this aromatic ring and this one. Whenever you add a Grignard reagent, the only place that Grignard reagent adds is to that carbon. Because when it adds to that carbon, it relieves the ring strain. It is inherent with that carbon. That makes sense? So the ketone ended up being more reactive than the aldehyde because the ketone was strained. The angles were all messed up. So when you added to that ketone, it relieved all that strain. So it made it so that ketone was way more reactive. So the simple reaction of adding a Grignard to an aldehyde in presence of a ketone, which should have worked, never, ever, ever worked. So what we had to do is we had to think, okay, I need to find a reagent that is even less reactive towards ketones than the Grignard reagent is. So I need to find something that doesn't want to react with ketones basically at all. And so what we ended up doing is, there's a reagent, I'll show you in a second, where you have usually silicon. It can also be, the other version of it can have a tin here. Right, and then you add a Lewis acid. So in the example that we have in the synthesis, it's BF3 etherate. And the point of the Lewis acid is it binds to the aldehyde. It makes that aldehyde positively charged. Right? So if you remember, like when you put a proton on an aldehyde, it makes it so it's easier to add to the carbonyl carbon because that oxygen is positive and pulls electrons away from the carbon, making that carbon more positive. Right? Then these silicon reagents are only ever able to react with aldehydes that have a Lewis acid stuck to them. So these electrons will come out and add to the carbonyl carbon, push electrons up. These electrons come down. And you end up adding an alum. So this carbon right here was this carbon right here. This carbon right here is this carbon right here. And there's some H plus in there to get rid of the boron. Fair enough. Right? So this reagent, allyl they never react with ketones. Ever, ever. So what we did was being able to so adding the, this is allyl tributylate. Okay. So adding the BF3 activated the aldehyde, made the aldehyde more reactive now than the ketone. Right, so we got the reactivity to flip back to favoring the aldehyde, and then we had to use a reagent that then also was very specific for reacting with aldehydes instead of ketones. So even though like base reactivity, aldehydes are more reactive than ketones. If things in your molecule change, if there's strain, if there's sterics, if like the aldehyde's hard to get to and the ketone's easy to get to, you can flip the reactivity that you're expecting. So it doesn't always work out the way that you think it should, but you can usually find some sort of workaround. So our workaround was to just use a reagent to make the aldehyde more reactive and a reagent that is specific for reacting with aldehydes and not ketones. So together we were able to then pick for the aldehyde to be the one that was reactive and not the ketone. Now, we wanted to do a ring closing metathesis. We want to take this double bond and have it react with another double bond to make this ring. The problem is, with using the owl group, I have one too many carbons now. So if I count, remember, in the simplest sense, olefin metathesis, it's the inside carbon gets bonded to the inside carbon. Went too far. Science has gone too far, man. There you go. Right, so, There it is. So if I count 1, 2, 3, 4, 5, 6, 7. I've got one too many carbons, right? I need to move this double bond. I need this double bond to be over one carbon. I need it to be over here. So that was the point of this reagent, was it moved the double bond over one carbon. So the metal associated with the double bond gave it a hydrogen and moved it. We'll go over how that works. And then I used this cross metathesis catalyst, and then that allowed me to make this ring. So right inside of the double bond, new double bond is here. Inside of that double bond makes a 6-membered ring. So we're going to go talk about this in a second. We'll finish this off real quick. Everyone remembers Des Martin from Organic 2, right? Oxidizes primary alcohols to aldehydes, oxidizes secondary alcohols to ketones. That's all it does. So I had a secondary alcohol, oxidize it to a ketone. Stryker's reagent. So what I had here was actually just show you a simplified version of this. See, we're all on the same page. So after I oxidized that, I had this. We're not going to draw the whole thing. We're going to draw the part that matters. I had that. This is, remember, this is an eno, right? Ene from the double bond, O from the ketone, eno. And then Stryker's reagent does 1,4 reductions. So we didn't get into this too much in Organic 2, but enones have unique reactivities. So if we number, up here, if we number all the carbons in an enone, or all the atoms, 1, 2, 3, 4, you can do what's called 1,2 addition, where you add stuff to the ketone. So say we add a Grignard reagent, like R, MgX, then H plus. You add your R group to the carbonyl carbon. This is a 1,2 addition. Right, you added your group to carbon 2, and you effectively put a hydrogen on carbon 1. Stryker's reagent, it has copper in it, and copper promotes 1,4 additions, which means you're adding something to carbon 4. So what happens is you end up with, you add a hydrogen, O, and then metal on your oxygen. That's your 1,4 addition. You added something to carbon 1 and pushed electrons, you added something to carbon 4 and pushed electrons onto the oxygen, which is number 1. When you add acid, this just gives you your ketone back. So 1,2 addition is adding directly to the carbonyl carbon. 1,4 addition is adding to the end of the double bond furthest from the oxygen. So Stryker's reagent promotes 1,4 addition. It adds hydrogens to the double bond, the carbon-carbon double bond, as opposed to adding a hydrogen to the carbon-oxygen double bond. So it's a selective reductant that only works on enones. I was tested not COVID-19. Safe. All right. So you ever hear 1,2 versus 1,4 addition? 1,2 you add to the carbonyl, 1,4 you're adding to the carbon of the double bond. So Stryker's reagent, its job was to take my enone and turn it into just the ketone. It was to get rid of the double bond. All right. So it does that, and then the last thing, share screen. And then the last step is adding CAN, which is short for, you don't have to write this down, but just to like let you know where we're working in terms of, this is short for cerium ammonium nitrate, which this basically takes these two groups and oxidizes them both to ketones. That's how you get what's called a quinone. So, whoop. I feel bad whipping back and forth, but it's the only way we can kind of do this and have it make any kind of sense. Because I feel like if I just talk, I lose, it's too much. And if I just write, then you're losing context. So I'm going to do my best here. So if you have something like this, and you add CAN, it turns this into that. And this is called a quinone. And these are kind of bad for you. So part of why benzene itself's not bad for you, right? Benzene doesn't cause cancer, but your body turns benzene basically into something that can turn into a quinone and then go back. And when it goes back, it rips hydrogens off of your DNA, and that's what causes cancer. So benzene is a bum rap. It's like dihydroxy benzene. That's the problem. So that's the end of the synthesis. What I wanted to do is I wanted to use the end here to talk about olefin metathesis. Right? So I wanted to talk about this step here. So using this catalyst to make this ring. Right, so that step really ends up looking like this. And everyone who had me for organic has seen some version of this before in organic 1, right? So I'm sure. Yeah. Sorry. There we go. Right, and you may remember Krebs 2 catalyst, right? And the job of this is it takes the inside carbon of one double bond, the inside carbon of another, over here, and it chews off the ends and it sticks the insides together. So this is going to be 1, 2, 3, 4, 5, 6. Okay, so I'm going to make a 6-membered ring. Blue carbon now bonded to green carbon. And there you go. Right. But I want to kind of take this. We did like very, very, very simple versions in Organic 1. And we never talked about like how it actually works. I was just like, magic. Right? So we're going to kind of talk through a little bit of the history and then the mechanism and show some more examples. Just to kind of give you a fuller understanding of this reaction. Oh, I guess I should also we can have a little story time here. So in somewhere between like 2007 and 2010, I think, everyone who did palladium cross-couplings, all these named people, most of them got a Nobel Prize. And they gave like a Nobel Prize to the developers of cross-couplings as a group. I do believe 1 or 2 of the people who did the early development died. And Nobel Prizes have a rule that they don't give awards posthumously. So that made it so they didn't have to give so many Nobel Prizes. They were down a few people, so they were like, okay, fine, now we can give palladium cross-couplings a Nobel Prize.
I'm really good at dropping things today. Wow.
Cool. An issue. So they gave everyone Nobel Prizes. And is it Robert Heck, who developed the Heck reaction, had like just quit chemistry in the 80s. He developed this reaction, had problems getting funding for a while, and just gave up. So they called him, I think he was living in the Philippines, tending like an orchid garden. And they were just like, yo man, you got the Nobel Prize. He's like, cool, I'm gonna go back to my garden now. He got more hyped for it later. But he had developed this reaction and then wasn't able to get funding anymore. And so just left chemistry. Like 10 years after he developed this reaction. He was like, well, I can't get funding anymore, I'm done. I'm gonna go live with my Filipino wife in the Philippines and just like be chill. Shit, man, live your life. Right. So, and he was at the University of Delaware when he did it. So I was at Delaware State shortly after he got this. So like, it was a big thing in Delaware. It's like, oh, and like Delaware's the size of like Horry County. So like, it's like, oh man, there's a Nobel Prize winner in Loris. Is basically what it's like. Like, oh man, they're like right here. Okay, so we are going to talk about olefin metathesis. Olefin metathesis also another thing that got the Nobel Prize. Just banging out Nobel Prize reactions. So, we've already talked. I just smashed for all of you who are like, you might have saw that. For all of you who are on Zoom, I just smashed my head quite loudly on the screen, on the projector screen. So, if I become disoriented, it's not that I've developed symptoms of COVID. It's that I just concussed myself. So, I appreciate your concern either way, but you don't have to turn me into Lori Cox in HR. It's just they smashed my head. Okay. So, the reaction takes 2 double bonds and puts them together. Like, that is the baseline of it, right? And it's really powerful, and it really changed chemical synthesis because usually to make bonds, you had to install a handle. You had to install some functional group that you could use to make your bond. Even in like the cross-coupling reactions, you had to install a halide and you had to install a metal, right? But for olefin metathesis, you just had to have a double bond. And a lot of times, double bonds are like where we start when we want to add functional groups, right? You learned a whole bunch of ways to turn double bonds into halides and turn double bonds into alcohols. You had all these ways to turn double bonds into other things. They're kind of our like one of our stock base starting materials for building up complexity. So instead of having to actually react with our double bond and turn it into something else and then make a bond, this allowed us to just make a bond with a double bond. Right? So what's great about these reactions is double bonds are really stable, right? They're normally not super reactive. So, right, they're easy to get starting materials and they're easy to work with. So there are things that are bench stable. You can just leave them in a bottle and they're not going to do anything, right? So that's good. There's no bases used, so you don't have to use a strong base at all. So that increases what functional groups can be present in your molecule, right? So you can have ketones and aldehydes and halides in your molecule because the only thing that is going to react with your the only thing that your catalyst is going to react with is the double bond. Everything else is just along for the ride, right? And it's catalytic in the metal. So you're only using a small amount of the metal, and you just turn over the catalyst over and over and over again, and you make all your bonds, but you only use a small amount of metal. So there are really like 3 or 4 catalysts that do this type of reaction. 3 or 4 main ones, right? So hopefully you can read these. I found out that that all of my old PowerPoints are no longer ChemDraw files, so I can't edit them anymore. So I just had to work with what we had here. So there's the first metathesis catalyst is the Schrock catalyst, and it uses molybdenum as the catalyst, as the metal that does the actual reaction, and it's really reactive. It reacts with a lot of double bonds, but molybdenum catalysts are, 1, kind of hard to make. 2, this compound doesn't like functional groups, so it doesn't work in like complicated molecules because it wants to go react with your ketones and your alcohols, and you have to use it in like a glove box. So if you're on campus, if you look into Dr. Goodwin's lab, he's got a big box that has gloves sticking out of it, a glove box. And the point is it's like in any movie you've seen where there's like a dangerous thing, right? The thing is, so this catalyst is so reactive towards air and water that you've got to put it in this box that only is filled with like nitrogen or argon and no water and no oxygen. And then you have to stick your hand in the gloves, and then you have to work with the compound in this inert environment, because if you were to open it just in the lab, it would decompose and would no longer be the catalyst, right? So that is a huge barrier to using the catalyst is, well, I've got to now get my stuff that is outside the glove box into the glove box side. Then I have to stick my hands in the gloves and I'm going to get all sweaty and gross side. I'm going to have to like do all this stuff. Then I'm going to have to get my reaction back out of the glove box side again, right? So that's a lot of extra steps, and it makes a catalyst like this not very like user friendly. So people were like, oh, hey, that's really cool. But I've got to do what now? I've got to like make this thing in a glove box. then I've got to get all my stuff in the glove box. No, we'll wait for something better. And then something better came along. That is Grubs 2. Now, all this stuff that I have around the catalyst, right? Anything that's stuck to a metal is just a ligand, right? So we talked about palladium catalysts having different ligands around them, how that changes the reactivity. All three of these next three, 1, 2, 3, all have ruthenium at their center, right? But they have different groups around the ruthenium. They have different ligands, and those different ligands change how the metal behaves, right? So this first one, I guess the only thing you don't know is CY. And so CY, I am 99% sure, is cyclohexyl. So this catalyst is, right, it's ruthenium with 2 chlorides, this, and then PCY3, 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 3, try again. These are phosphorus with 3 cyclohexanes around it. All right, and phosphorus, if you remember, phosphorus is under nitrogen on the periodic table. So just like nitrogen, phosphorus has a lone pair. So phosphorus uses its lone pair to make a bond to the metal. So that's how it binds to it. All right, so this is Grubs 1. All right. So that is the first version of the Grubs catalyst that was published. Now, Grubs 1 is a bit of a misnomer, just because I'm sure they made like 100 different versions of this catalyst before they found one that worked, right? So this is Grubs, the first one we thought that was good enough to publish. So it's Grubs 1. Okay. So sorry. Let me scare you there. Second. All right. So this is somewhat unreactive. It's not nearly as reactive as a Schrock catalyst. It takes a little more oomph to get it to go. But what's good is it doesn't react with other functional groups. So it's good for complicated molecules because it will react with the double bond in the presence of a ketone or an alcohol or an amine, right? And you could just use it in a fume, right? So as opposed to having to go into the glove box and be like, oh, right? You could just go take it off the shelf or out of your desiccator and use that catalyst, weigh it out on a balance just like in a regular lab. So super easy, no big deal. All right. Now, Grubs 2, we changed one of the ligands on the catalyst. Right, so Grubs 2, we've replaced one of the phosphines with, and there's so many things that you guys, I was going to say like an N-heterocyclic carbene, but now I've got to explain that. You replace it with an N-heterocyclic carbene ligand. So you replace the phosphorus with this group here, and that changes the reactivity. Everything else stays the same, but changing that one ligand, now it's more reactive. It's tolerant of functional groups, but it still maintains the ability to use like in the hood. Right, so carbenes are weird. As I hit my head again, like hopefully there's nothing important up here, because I'm just like smashing it all the time. Right. So I'm going to change this line here. So So a carbene is a carbon that has basically a positive and a negative charge on it at the same time. So it's a carbon that has a lone pair, but it also has an empty p orbital. So these can simultaneously be added to the positive charge and add to things with the negative charge, right? So they're often written like, so that would be, so in that ligand, you would write it just as like having a lone pair like this. So they're not real stable, so you put them beside heteroatoms, like nitrogens, and those nitrogens help stabilize that carbene. So what the carbene does as a ligand, right, is when it's on the metal, right, it can use its lone pair to make a bond to the metal. But it has the empty orbital. Metals are weird, right? So I don't do inorganic chemistry because metals are weird. Is that when we think about carbon, we're like, you make 4 bonds. We're good, right? 4, right? You have 8 electrons around you. Metals have 18 electrons around them, right? So this metal can simultaneously be making a bond with the carbon and donating electrons back into that carbene and making a stronger interaction. It makes part of a double bond. So carbenes are just weird in terms of like structure, but they make really good ligands. They stick to things well, and you can change the groups on the nitrogen, and that changes the electronics and stuff. The take home here is we changed the ligand and we got a better catalyst, right? So Grubbs 2 is kind of the gold standard of metathesis catalysts. And people have taken to modifying the Grubbs catalyst some to get slightly different reactivity. So the Hoy-Beta Grubbs catalyst down here, they actually remove the phosphorus ligand entirely, and they have an oxygen. So what we're going to see how these catalysts work is they react with this ruthenium carbon double bond. They react with that, and that group kind of falls off. It goes into your reaction. And when it falls off, what happens eventually is when your catalyst stops working, it's because your catalyst starts to fall apart. So with the Hoy-Beta Grubbs catalyst, when the reaction happens, you have this did it again. Right? Here's this phenyl group. Here's that same phenyl group. But the phenyl group has an oxygen on it now. So that oxygen acts as the ligand. So when that phenyl group falls off, it never gets too far from the ruthenium because it's still stuck to it. And so it can always come back and remake the stable catalyst. So Hoy-Beta Grubbs catalysts last longer in solution because they never fully lose that phenyl ligand. It can always rebond. So we're going to walk through the mechanism of an olefin metathesis, right? So yes. So when I posted the new set, it was all the olefin metathesis stuff plus a few things that I added to try to make the palladium stuff a little clearer. So you have all of this stuff. So we start out with our catalyst. I'm gonna leave it like super like vague, like in the slides, where it's just some ligands, and do I have phenyl up here? Just R phenyl. Some ligands and ruthenium double bonded to basically styrene, right? Give me 1 second. I need to go blow my nose. Take off my mask. Look at it. Talk amongst yourselves. So, what you need to do is find your pen. Is you have to load the double bond that you want to react, that you want to do your metathesis with, onto your catalyst. So you do that. You have. Try this around the right way. I do. You take your R group, and you have your metathesis your catalyst react with it, and you do what looks like it's called a 2 plus 2. These electrons go here. These electrons go there. Let me fix that error because it looks like a travesty. And so what you end up with is this four-membered ring. A metallocyclobutane, a cyclobutane where you replace one carbon with a metal. Right? And this is a 2 plus 2 reaction, effectively. So if you remember Diazono reactions were 4 plus 2s, right? Because you took 4 electrons from here and reacted with 2 electrons there. That was a 4 plus 2. 4 plus 2. This is a 2 plus 2 because you take 2 electrons from the ruthenium carbon double bond and 2 electrons from this double bond. So it's a 2 plus 2. Once you get here, this then will fall apart. Try to draw the arrows in the right order because they do matter. Right? Yes. Yeah. So these electrons go here, and these electrons go there. So what you end up doing is you break the carbon-ruthenium bond that you started with, and you make a new version of the catalyst that now has your R group, the thing that you want to do the metathesis with, stuck to it. So what this looks like in the end is you end up making this. So now you have basically a new version of your catalyst. Sorry. You have a new version of your catalyst plus you've made styrene. And now this is going to react with the next olefin. So this styrene that you spit out This is why the Holy Beta Grubbs catalyst has that oxygen. Go back for a second. Screen share. Screen. Right. It has this oxygen here because when you do that step and styrene falls off, in Grubbs 2 and Grubbs 1, styrene is just gone. It just goes off into your reaction, never to come back. Holy Beta Grubbs, because there's this oxygen here, when that styrene falls off, it's still held to the catalyst. So if you ever end up with something on your ruthenium that's not very stable, it can just reform the bond to the aromatic group again, because the aromatic group's always just hanging out right by the reactive center. So anytime it gets to a point where there's nothing for it to react with, or it's not very stable, it just reforms as a stable catalyst and keeps going. So it just makes it so the catalyst hangs out in solution a lot longer because it doesn't fall apart as easily. Okay. Back to the whiteboard. All right, so this ends up being the catalyst that actually goes into the catalytic cycle. You load your one double bond on, and then this is what reacts. So what happens here is you take your ruthenium catalyst, right, with your R group on it, and move it over. Right, then it reacts with whatever your next double bond is, whatever the double bond you want to react with next. And it does the same thing that we did before. It does that 2+2 reaction. Electrons come up, electrons down. Make our metallocyclobutane again. And then this falls apart. I want to wave this way and that. And you make your double bond. So I'm going to actually wedge this. Right, they're on opposite sides of the metallocyclobutane. They end up on opposite sides of the product. So this species right here, right, it's still a ruthenium with a double bond. It can go do the reaction. It's not very stable. So this is usually where your catalyst runs the risk of falling apart, is when you just have a CH2 double bonded to your ruthenium. It can fall apart here. So what happens is this then will react with oh no, did I not? Sorry. Give me whiteboard. We'll make you give you one. Let me go back. Sorry. Yeah. Sorry. I somehow made it so the in-class people couldn't see the whiteboard. You guys, Zoom people, whiteboard. In-class people, nothing. I'll figure this technology thing out, I don't know, in 2022. By that point, I'll be just replaced by like virtual Wakefield. Like VR Wakefield will be great. You just put on a little visor and you just get this. So, yeah, this is the part right here that I was saying. This is where your catalyst can fall apart. this thing is not very stable. So your hope is to kind of keep the reaction going to get to the next cycle so you can make the next product, is you want this to react with your R group again, do the 2 plus 2, and get you back to that starting this, and then you generate ethylene, which is a gas. It will actually bubble out of your flask. You can actually sometimes see little bubbles of ethylene if the reaction is fast enough. So that's kind of the less clean version of it. I'm going to show you the nice version of it. I know I've kind of flashed through it a few times. And what I want to point out here is I've drawn one version of this, right? We drew one version. The thing to take away though is the olefin metathesis catalysts aren't selective. So we have here that it's reacting with R1, and then later on it reacts with R2. It could react with R2 first. It doesn't really discriminate. It just will react with the first double bond it runs into. And the way we have this drawn leads to product. Like this structure right here, when you undo the 2 plus 2, right, that gives you your two things bonded together. But it also can react like this, right, where your two things end up not bonded together, right, where the two R groups end up apart. And what the Grubbs catalyst does is it just keeps doing the reaction. And what determines if your product is formed is the Grubbs catalyst keeps reacting until it makes a stable product. So once it makes a stable product, and that product is not very reactive with the Grubbs catalyst stops messing with it. So putting these two together and making them trans, that makes the most stable product it can make, and that becomes less reactive. And so the Grubbs catalyst stops reacting with it. So you're getting a whole bunch of different permutations where you're just sticking carbons together, and every so often, through the miracle of thermodynamics, you make something that's stable, and the Grubbs catalyst goes, fine, I won't react to that anymore, and that's your product. So we've drawn the one catalytic cycle that leads to product, right, that puts these two groups together. But for every one of these cycles that gives you product, there might be 100 that just change this carbon on the double bond and this carbon on this double bond, just swap them. And those carbons will swap back and forth, back and forth, back and forth. And then every so often, you make the product. So Grubbs reactions are kind of controlled by two things. They're controlled by kinetics, how fast the product forms, and thermodynamics, how stable your product is. If your product forms quickly and is stable, that's the product you're going to get. If your product takes a long time to form but is stable, you'll eventually get it. If the thing you want to make isn't very stable, you're never going to really get to make it because the Grubbs catalyst is just going to see it as another double bond. Everything to the Grubbs catalyst is a double bond that it can react with until that double bond is too stable or too hindered that the catalyst can't get to it. And then it goes, I won't mess with that double bond anymore. I'll go find another one that's easier to mess with. So you need your product. Grubbs reactions usually favor trans double bonds because trans double bonds are more stable. Right? So it's like, hey, I'm going to make the most stable version of this I can. Trans. Cool. That's over here now. I can't react with that anymore. I'm going to go react with stuff, and eventually that happens enough that you make something that you want. Now, because we're scientists, right, there are versions of these catalysts that specifically make cis double bonds because they've changed the ligands around the metal. Don't care that much. right? You go on SciFinder and you look up metathesis make cis double bonds, you can find that, right? But how they actually work is all the same, the actual mechanism. We'll stop here. We'll go over types of metathesis and some examples on Tuesday. Hopefully I'll have some slides about making double bonds. And we'll start going over how you make double bonds, because I think we have a reasonable number of ways to use double bonds, right? So we need to show you how to make some double bonds that are more than just like Davidic reaction and heating alcohols and sulfuric acid. So, any questions from the Black Box Society? We good?
No.
Okay. Well,
We're good.
I will see you guys on Tuesday.
Thank you. Have a great weekend.
You too.
Thanks.
Okay. Bye. I dunked myself pretty good.
It's just an accident trying to
Yeah, your coffee went to the big Starbucks in the sky.